Okay, so as I was saying, in this one, right, Fg equals mg, dividing both sides by m, we use Fg equals mg when we're trying to find our weight. And the g is the gravitational pull from the Earth, right? So this is my mass. So this is my mass. So it's the mass being brought into the field. In this case, it would be like the Earth's field. Whereas this mass would be the mass of the Earth itself. So the mass creating the field, right? And so the same thing is true down here. The Q on the bottom is the charge being brought into a field that already exists, that's created by another charge. Whereas the Q on the top is the charge creating the field. So this is charge creating field. And this is a charge brought into the field. Okay? So far then, in this review preview, we have three equations. We have FQ, the electrostatic force, where Q is a charge, is equal to K Q1 Q2 over R squared. We have E, which is the electric field, and that's equal to either KQ over R squared, or it's equal to FQ over Q. What we didn't talk about was what are things measured in. Well, I think you know that F is measured in force. Last sheet there, last video, I said charge was measured in coulombs. And so K, its units, so it's, I'm going to just write for time's sake, 9 times 10 to the ninth, Newton meters squared per coulomb squared. Those units should make sense because then when I put them in here, the per coulomb squared will cancel the coulombs from the Q, meter squared will cancel the meter squared from the R, and I'll left with newtons, which is what force is measured in. Okay, what is electric field measured in? Well, force is measured in newtons, so this has to be in Newton. Charge is measured in coulombs, so electric field is measured in newtons per coulomb. There's not a name for that, it's just newtons per coulomb. If we did the same thing over here, we'd have Newton meters squared per coulomb squared times just 1 coulomb, so there'd be 1 coulomb left on the bottom, and the meter squared would cancel with the R's, and again we'd be left with newtons per coulomb. Okay, so now the one thing that's different, electric fields to gravitational fields, is the fact that they could be attraction or repulsion. Okay, so if I have a positive charge right here, then the field around it could be going in towards it or could be going out of it, right? If I have the Earth, the gravitational field going in. We know that no matter where we put an object around the Earth, it is going to experience a gravitational force of attraction inward. But if I have a positive charge, then are these things that I just drew here, they're called field lines. And they show the direction of a field at a particular point. So if I have a positive charge, how do I know if the field lines are going in and out? Because won't it depend on if I bring a little positive charge in or if I bring a little negative charge in? The field lines would be going different directions depending on which one. This caused major confusion back in the beginning of time. Well, maybe not the beginning of time, but in the beginning when we began to figure all this out. And so scientists got together and said, no, we have to define it. So we're going to say that the field lines around a charged particle are always determined by the direction that they would point based on if you brought a little positive charge in. So if I bring a positive charge in, it's going to experience a push outward. And so the field lines around a positive are going outward because they would push outward if I brought a little positive guy in. This little positive guy we call a positive test charge. And the positive test charge is kind of like a little positive kid that hangs out with you often. You know, it's that little kid that you're like, I'm going to go watch TV, want to come? And they're like, yeah, yeah, yeah. Or I'm going to go to the store, want to come? Yeah, yeah, yeah. I'm going to go jump off the roof, want to come? Yeah, yeah, yeah. Like no matter what you say, they're positive, they're in for it. Okay? And sometimes you probably use them as a test. You probably send them into a situation. You say, hey, why don't you go ask, I don't know, your parents, my parents, whoever you happen to be hanging out with, if we can have pizza. So you send the little kid in, and you see what happens to the little kid. And depending on what happens to the little kid, it tells you the nature of the charge inside. It tells you the nature, positive or negative. If they're like, that's a crazy idea, we'd probably consider that negative. And the little kid will come out, whatever the little kid does will let you know. Okay? So a positive charge has field lines going away from it because it would push this little positive test charge away. And the little positive test charge, it's always tiny, and it's always positive, just like the little kid. If there was a negative charge here, and we brought a positive test charge in, always positive, always little, the negative would like it. And so the field lines around a negative test charge, a negative charge, are always, always, always inward. Okay? Now, sometimes we end up with charges that, like positives and negatives that are close to each other. And when we do, the field lines are going to overlap. Now, there's a few, or going to interact. There's a few rules about field lines. They can never cross, is one rule. The second rule is the closer they are together, the stronger the field. So when we look at the field lines, it's telling us about the strength of the field. Now it's true I can add a whole ton of field lines in here, but it doesn't matter. They're still going to be closest together, closest to the charge. And as you move away from the charge, they're going to get further apart. That means the field is strongest near the charge, and out here, further away, it's weaker. Okay, so the concentration or the number of field lines in a given space tells us about the strength of the field. Okay, field lines can never cross because field lines show you the direction that the field is pointing at a given spot. If they cross, it means the field's going two ways at once. You should try that sometime. It's really hard to go two ways at once. Okay, so field lines can never cross. So what that means is, if I bring two positive charges together, then their field lines are going to interact, but they can never cross. Remember, it's what the field lines are showing is what would happen to a little positive test charge if I were to put it at some point in the field around them. Well, this guy doesn't want it. It will push it away. And this guy doesn't want it. It will also push away. And the result will be the field lines around both of them will curve. I always think they look like spider legs. Remember, arrowheads are going out because that's the positive charges would not want this positive test charge, so it would be pushing it away. If I had two negative charges that were close to each other and I did the same thing, I put a little positive here, they would both want it. So the field lines are going to look very similar, except this time the arrows will be in, not away. They'll both try to draw it in. It's harder for me to put arrowheads on going in, just saying. Okay? Whoops, that didn't really cross. That was just the paper moving because one hand's holding the camera. All right. What if it's a positive and a negative that are brought near each other? Well, if it's a positive and negative, the positive doesn't want this little tiny charge and the negative does, so they'll actually work together. And the lines will look like this. Okay, so these are called field lines. Why the heck are we talking about them when we're supposed to be doing Science 12.2 and electricity was done last in Physics 12? Because we're going to get to magnetism, hopefully maybe by tomorrow. And magnetism, they have fields, just like electric fields and just like gravitational fields. And so again, we will be using field lines to show them, okay? So we have to understand the electric stuff and the gravitational stuff so the magnetism ones will make sense. All right, now if I can find some questions, I'll post them for you. If not,